Finding the electric field of a complex charge distribution usually means running into a wall of calculus, but there is a way to bypass the integration. By looking at the symmetry of a shape, we can reduce that math down to a single equation. To use it, we first need to understand electric flux. Think of flux like wind blowing toward an open window. How much wind actually makes it through depends entirely on how the window is turned. Face it head-on and you get maximum flow. Turn the glass completely sideways, and nothing passes through at all. To track this mathematically, we use an area vector. This is simply an arrow drawn pointing straight out, perfectly perpendicular to the surface. It tells us exactly which way our window is facing relative to the incoming field. This brings us directly to Gauss's law. It states that if you draw any closed imaginary boundary completely surrounding a charge, the total flux passing through that boundary depends on exactly one thing: the net amount of charge trapped inside. You can warp that boundary into a perfect sphere or a jagged blob. The exact same number of field lines will pierce through it. Because the shape of the boundary doesn't change the total flux, we have a massive advantage. If we carefully choose an imaginary boundary that matches the physical symmetry of our charge, the electric field aligns perfectly with our area vectors. The calculus cancels out, leaving us with basic multiplication. Let's apply this to an infinitely long charged wire. Because the wire is a straight line, its electric field radiates directly outward in all directions, creating a cylindrical symmetry. So we draw a cylindrical imaginary boundary right around it. We split this cylinder into separate surfaces to calculate the flux. Look at the flat end taps. Their area vectors point straight along the wire, perfectly perpendicular to the outward electric field. That means zero field lines pass through them. All the flux is isolated entirely to the curved outer wall, where the field and the area vector run exactly parallel. Now consider a flat, infinitely large sheet of charge. The physical symmetry changes, so our boundary has to change with it. Here, we use a small, flat cylinder called a pillbox that cuts straight through the plane, protruding equally on both sides. Notice how the geometry flips. The electric field points straight away from the flat sheet. This time, the field skims right past the curved sides of our pillbox, contributing absolutely no flux. The only places the field actually pierces the boundary are those two flat end caps. The entire strategy relies on this strict visual alignment. By picking a shape where every surface is either perfectly parallel or exactly perpendicular to the field, you eliminate the zero flux surfaces immediately and solve the remainder with simple algebra. Next, we look at a hollow, uniformly charged sphere. If we draw our imaginary boundary outside the shell, the math is identical to a single point charge. From a distance, the entire shell acts as if all its charge is concentrated right at the very center. This photograph shows a person safely inside a metal Faraday cage being struck by lightning. Because they are inside a hollow conductor, all charge lives on the outer surface. Any internal boundary traps zero charge, meaning the internal electric field is exactly zero. Things get more interesting with a solid, uniformly charged sphere, where the charge is packed tightly all the way through. If you draw a boundary inside this solid object, it captures a fraction of that charge. Pause and look at this setup. What specific mathematical ratio determines exactly how much charge is caught inside? Because the charge is distributed evenly, the amount trapped grows with the cube of the radius, but our boundary surface area only grows as the square. When you divide that cubic charge by the quadratic area, the resulting electric field increases in a perfectly straight linear line from the center to the surface. The structure of the object defines its internal environment. Hollow shapes create empty, shielded zones with no field at all, while solid objects generate internal fields that grow steadily the further you step away from the center. Let's put everything into a single, unified map. Here are all four major charge distributions side by side: the line, the plane, the hollow shell, and the solid sphere. These graphs in the top row show how the electric field behaves over distance. For the infinite plane, the field is perfectly uniform. The graph is a flat, horizontal line because the strength never drops, no matter how far away you get. The line charge, however, spreads out as it travels, slowly decaying as 1 over r. Down in the bottom row, these graphs map the 3D shapes. The hollow shell stays at 0 until you hit the surface, then drops off steeply as 1 over r squared. The solid sphere builds up its field linearly from the center, hits its peak at the surface, and then matches that exact same 1/r² decay. This is the complete map of Gauss's law applications. Right now, grab a blank piece of paper and sketch out these 4 setups and their corresponding graphs from memory. Connecting the physical geometry directly to the graph is how you lock this in permanently. Mastering Gauss's law reveals the underlying power of physical symmetry. Once you see the geometry of the universe, the complex math becomes a secondary detail.